40%, less than 50%, that is 40.6%, and ripple factor is 1.12. That means very high AC is present, whatever DC we are getting, right? So to change that one, or to improve the efficiency and reduce the ripple factor, we'll use full wave rectifier circuit. That means both the half cycles should be at the output. Then we can have little bit more efficiency and ripple factor also reduce. So in that such of that condition, we have taken center tap full wave rectifier circuit where the transformer is a center tap one. That means whatever voltage is given at the primary, at the output, it is divided into two parts, and one part is connected to diode 1, one part is connected to diode 2, and resistor across those two diode and center tap, the resistor is connected, load resistor. So today we'll see how it operates. Up to this, everything is clear, or anything you need to repeat? Guys, anything you need to repeat, or we'll proceed?
Proceed, sir.
Okay. So whenever we give AC signal, so let us say first negative half cycle is given, sorry, positive half cycle is given. So when I'm giving, let me draw here one AC signal like this. So this is positive half cycle, this is negative half cycle. Like in positive half cycle, it will continue like that. Now let us give this positive half cycle. So how I will represent? The lower side is negative, upper side is positive. So this is the primary side of the transformer. So secondary side also will get plus minus. Okay. Now again it is divided into two part, or two voltage will get. So to maintain that, because voltage means we need one positive terminal, one negative terminal. So here I'll put, this is negative, so I'll get here V, and this one is positive, here I'll get again V. Okay. Now you see diode 1 and diode 2. So diode 1 anode is connected to positive, and this negative is connected here. Okay. So diode 1 is positive, means P side is connected to positive and N side is connected to lower potential. Then diode D1 is on or off, or forward bias, reverse bias. Diode D1 is forward bias or reverse bias? Are you getting my point or not? Am I audible?
Sir, forward.
Forward. Forward means I can replace as short circuit. So I'll remove this one, and I can replace that one with short circuit. Now what about the diode D2? See, this negative is connected to here and positive is connected. This is positive and this is positive, this is positive, so this is connected here. So it is on or off?
Off.
Off means open circuit. So now if I see the current, what is the direction of current? Current will always flow from positive to negative. So we'll start from here. Now when it will reach here, it will go this direction or this direction? Downward or left side it will move? Current?
Left.
Left. It is open circuit, so current will move this direction. Like this, it will move. Okay. So this is for positive half cycle. Now when I give negative half cycle, this is plus, this is minus. So here we will get plus, minus. To maintain the voltage, here plus, here minus. Now just reverse thing will happen. That means this will be off and this will be on. You can see because plus is connected here, P side, so it will be on, this will be off. So look at here, look at this diagram. So this one I have explained, current is flowing this direction. Now again current will flow from positive negative. So you see this green arrow mark, that is moving like this. Earlier it is moving like this. Okay. Whatever I have explained, the same thing is written here and direction is also given. Now you observe this two operation, that means when the diode is, or when we give positive half cycle, when we give negative half cycle, across the load resistance, the direction of current flowing is same or opposite? This direction?
Yes, sir.
This direction. So current is moving in same direction or opposite?
Opposite,
Across
sir.
RL. Across RL. This is the RL. Current is flowing this direction in positive half cycle. Current is moving in this direction in negative half cycle. Right? Like this, like this. So now tell me whether it is moving same direction or opposite direction. Same. It is moving from right to left. Yes or no?
Yes, sir.
And we assume that diodes are ideal diode. There is no drop across the diode. Then what will get? Positive half cycle and negative half cycle both in same direction. You see here, this is my input V in. Then for positive half cycle, we are getting 0 to pi, then 0, then 2 pi to 3 pi, then 0, then it will continue like this. Negative half cycle will get 0. That means here what will be on? You see, D1 is on and D2 is off. That is your first condition. D1 is on, D2 off. D1 on, D2 off. This is like half-wave rectifier operation. Second one, when negative half cycle given, then D2 on and D1 is off. So D1, this one, and this is D2. D1, D2. Like that, it will continue. So if I combine both these things, then I'll get this type of waveform. Or you can see here, when D1 is on and D2 off, what I am getting here, positive half cycle, same signal I am getting. Okay. So this is due to D1. Now once positive half cycle over, then we will move to the negative half cycle. So negative half cycle means D2 is on, so current will flow in the same direction. So I am getting D2 here. That to positive half cycle. Again D1 will be on, so I am getting positive half cycle. Then again negative half cycle, D2 will on, so again I am getting here positive half cycle. So you see here, positive, 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 all are positive because the current through the resistor is only flowing from right to left. Same direction current is flowing. Got it? Earlier in the half cycle negative means half wave rectifier, what we are getting? Only positive half cycle, then 0, then positive half cycle, then 0, like this. So what is the difference between these two? This negative half cycle, which is clipping here, now it is converted to positive half cycle. So that's why the current is flowing in the same direction, and at a time, that means when this is operating, this is off when this is off, this is on. That means at a time it is combination of two half wave rectifier circuit, but in same direction. Is it clear? So if I note down here the time period 0, pi, 2 pi, 3 pi, 4 pi. Input signal like this. This is 0, pi, 2 pi. Now tell me what is the time period of input signal and what is the time period of output signal.
Sir, input signal is 2 pi and output signal is pi.
Pi. Input signal 2 pi because from here to here it is repeating, and here to here it is repeating. So here it is 2 pi, here it is pi. Now what about frequency?
1 upon
1 by 2 pi, 1 by pi. Then let us take, this is F out, this is F in. Okay, what is the relation between F out and F in? F out is equal to
2 into
F in. Just time period here reduced, right? So frequency will increase. So how much it is increased? 2 times it is increased.
Yes, sir.
And this is pulsating in nature, still pulsating in nature. But what is the difference here? Half wave rectifier, only half cycle we are getting. Here both the half cycle we are getting. So by looking at the graph only, you can say the efficiency must be greater than half wave rectifier circuit. Okay, because only half cycle we are getting in the half wave rectifier, so we are getting 40.6. Here both the half cycle we are getting, so must be double than that one. So that will be 81.2. Mathematically also will calculate, but observation says this. And ripple, you can see previously what are the ripple? We are getting like this. Now peak to here, the gap is more, but now the ripples are little bit less. So we also calculate this ripple factor as we have calculated in half wave rectifier circuit and compare. Now whatever derivation I have done in the last class, the same derivation will be there, but only change you will do it here, the time period. Here 2 pi, here pi. What is the time period we have taken in half wave rectifier circuit? That is 2 pi. In half wave rectifier circuit, we are getting 2 pi because the signal is like this. So 0, pi, 2 pi, here to here it is repeating. So here it is a t. Now only this time period will change. Now look at here the derivation what we have done for IDC, I Rms, I average. How we have calculated. Do you remember all these things? Now tell me what changes you will do in this derivation. What change you will do? What is this one?
2 pi.
2 pi, that means time period. We integrate and average with respect to time period. So
Yes.
for half wave rectifier that is 2 pi. For full wave, what is the time period we have calculated now?
Pi.
Pi. So this 2 will be removed from here. If you remove this 2, then what will get here? This is how much we have calculated 2 cancel, and we are getting 2 sorry Im by pi. Now what we get? 2 Im by pi we will get or not? The denominator 2 is there. If 2 will be not here, then what will get? Earlier what we have found out, Im by pi 2 pi into 2 to cancel, then we are getting Im by pi. Now this 2 is not here, so what will get? If you confuse, you calculate now. And then you derive all these things by taking limit as pi. Same procedure, only in place of 2 pi you put pi and derive it. Tell me what is the answer. Have you got any answer? Are you doing or not? Yesterday while deriving, I told you this same procedure will again follow in full wave rectifier circuit, only limit will change. So now change the limit and find the answer. Tell me what is IDC. No one is able to solve.
Sir, IDC 2 Im upon pi.
2 Im upon pi.
Is it correct?
Of course. So here 2 is not there below in the denominator Im by pi, so we will get 2 Im by pi. Very good. What is your name?
C1, sir.
Okay. Now we'll go for RMS calculation. Now you calculate the same thing by taking 1 by pi integration 0 to pi IL square d omega t. Same procedure, and tell me what is the answer.
VDC, sir.
No, IRMS for AC. DC you already calculated, na? IDC, what you have got? Let me write it here. What you told. IDC, what you have got? 2 Im by pi. This one, na?
Yes, sir.
Then we can calculate easily that power PDC equals to IDC square into RL. Now we need to calculate I RMS. Okay. So how we will calculate? Yesterday I have derived here. So this is the procedure.
Yes, sir.
Here we have done one mistake. This is 2. Okay. So Im square by 4. So same thing you will again repeat by taking 0 to pi, 1 by pi, because here also the limit is pi and time period is pi. Tell me what is your answer, IRMS.
Sir, Im upon root 2.
Im upon root 2, because here if you remove 2, then it will be Im square by 2, and when you take IRMS, then it will be Im by root 2. So okay, so this is only change if you take the limit. So whatever I have explained, everything is written here. Now PDC equals to IRMS, PSC first it is calculated. So input power or AC power equals to IRMS square into RL plus RF. So IRMS you have calculated Im by root 2. You can also calculate in terms of voltage. So your answer is PI equals to IRMS square into RF plus RL. So you replace current or voltage. Okay. Then PDC, IDC square into RL, same procedure what we have followed in the half-wave rectifier circuit. Then 2 Im by pi, here you can replace as voltage 2 Vm by pi. So this is your PDC. Now if you find efficiency, so what you will get, PDC by PAC into 100%. So PDC is 2 Im by pi whole square RL divided by Im by root 2 whole square RL plus RF into 100. So if you open the bracket, then Im square cancel, and here you will get 4 by pi square, and below here 2. So we will get here 8 by pi square into RL divided by RL plus RF into 100. So if you divide by RL, this will be RL, RL, RL. So it will cancel. So here, as we have taken in half-wave rectifier, RF is much smaller than RL. That implies RF by RL is much less than 1. So finally what we will get, eta equals to how much?
8 by pi square into 100.
8 by pi square into 100%. So last in half-wave rectifier derivation we have got 4 by pi square, that is 40.6. It is 8 means 2 times of that one. So you'll get here 81.2%. Okay, so this is your efficiency, you can see. Now ripple factor, same way you can calculate. Ripple factor is IRMS by IDC whole square. If you replace all these things, then you will get 0.48. Okay, 0.48. Now you compare this one with half-wave rectifier circuit. In half-wave rectifier we are getting 40.6% as efficiency. Now it is double. Ripple factor 1.21, now it is 0.48. 0.48 means the AC component is more or DC component is more here. What we have calculated, IRMS test by IDC is your
DC more.
AC more.
right? So compared to half wave, we'll get less ripple in the full wave rectifier circuit. So it is improved. So efficiency double and ripple factor also decrease. But what is the drawback of this circuit? Can you identify here? In this standard type full wave rectifier circuit, what is the drawback? Efficiency improved, ripple factor decreased. Operation we have understood, we have calculated efficiency and the ripple factor, but do you find any drawback in this circuit? Anyone guess?
Two diodes needed.
A diode cost is very less, means maybe 1 to 5 rupees. So 2 diode it is okay, because we are getting 2 half cycle, means obviously we require 2 diode. 1 half cycle means 1 diode. So that is obvious thing. Any other drawback you are?
So the graph is not uniform.
Which graph? No, graph is uniform na. You see?
सर थोड़ा कॉम्प्लिकेटेड है इसका हाफ वेव से.
सर मतलब कंटिन्यूअस सप्लाई नहीं मिलेगा, वो कम होता रहेगा फिर बढ़ेगा फिर.
हाफ रेक्टिफायर तो ऐसे होता है ना, हाफ रेक्टिफायर में कैसे होता है, बढ़ गया ठीक है, फिर जीरो, फिर तो इससे तो अच्छा है ना ये. both the half cycle, here we are getting positive half cycle, then 0, then positive half cycle. So change here, suppose 5 volt 0, then 5, then 0, but here we are getting somewhat almost same thing. Any other in circuit you may find, that is okay. In circuit do you find any problem? See here, this part, if you don't have this type of transformer, then can you able to design this rectifier circuit?
No, sir.
So normal transformer, you know, primary side, secondary side. So this is a special type of transformer which is from the center it is tapped. Okay, if you don't have this center tap transformer, then you cannot design this circuit. So that is the major drawback in this circuit. Okay, so if we don't have this type of transformer, or if I have only normal transformer, as like you have already discussed, this type of transformer, then how to use or how to get full wave rectification. Then we will move to other type of rectifier which is called as bridge type rectifier. Okay, it is not in the slide. You just write whatever I will write here. Bridge type full wave rectifier. So the circuit, if you see, this is your transformer. I have just tilted it, and secondary winding, this is my secondary winding. From secondary winding, two diodes are connected like this. Then again here then end to end I'll connect, and one resistor is connected. This is your RL, this is your input AC, the transformer. Let me name here, this is D1, D2, D3, D4. So here I don't require any center tap transformer. Using normal transformer I can design, but extra 2 diode is needed. So 4 diode circuit, and this is like a bridge connection. So that's why it is called as bridge type full wave rectifier circuit or bridge full wave rectifier circuit. Now if you have drawn, let us analyze it. So my input signal is like this. Now when positive half cycle is given, so let us take, this is bottom side, this is top side. So I am giving minus plus, or let me give in the secondary primary side minus plus. So I'm getting here minus plus. Now see the diode connection. Which diode is on and which diode is off, you tell me?
D1 is on, D2 is off.
D1 is on because anode is connected to positive or higher potential, cathode is connected to lower potential. D1 is on. So this is on. Then D2 off. What about D3 and D4?
D3 on, D4 off.
D4 is off.
D3 on.
D4 is off. D3 is, this is negative terminal, it is connected to N side, so it is on. Okay, so I can again redraw this circuit like this. So it is on means short, then it is off, then it is off, then it is on. Then this is the resistor RL. So minus plus minus plus. Now see how current will flow. Current will flow from right to left, so I am moving from here, then I am reaching this point. So I'll move downward or upward. The current will move. Huh? This direction or this direction current will move?
So upward.
Upward. So current will move this direction. Then I am reaching here. Then across the RL or through open circuit it will move.
So across RL.
So current will move like this. Then reaching here. So left side or right side?
Right side.
Then here up or right, left from this point?
Left.
Left. Now loop is complete. So finally current is moving across the RL like this. So I'll get IL into RL, that is output voltage. So here I'll get output voltage like this for positive half cycle. Understood? Vm, this is V naught, Vm, so 0 to pi. Positive, we are getting positive. Now when negative half cycle given, so let me take another color, pink color I am taking here. So plus minus, so here plus minus. Now tell me which diode is on and which diode is off.
So D2 on. D2 on.
Is off.
D1 off.
D2 on, this is off, here it is on, here it is off. Again you redraw this one. Have you drawn this all this circuit? I am just showing here the pink line. So current will start from here, it will move this point, then it is off, left side it will not go, so it will go this way, then it will come here, then this is right side is off, left side is on, so it will move like this. Understood? You again redraw like this. I have not drawn again because it will take time. So that's why I have shown only this way, this pink line. So current is flowing again in the top to bottom. So I am getting here another half cycle from pi to 2 pi. Clear? So actually 3 diagram you draw. First one original circuit, then this is when positive half cycle given, then negative half cycle, again redraw it by taking opposite way and show that current direction as I have shown here, and this is my output signal. Is it understood? Operation of the circuit.
Yes, sir.
Now, while calculating efficiency and ripple factor, is the same procedure will follow or something different? The time period you check for center tap and bridge type, the time period is same or not?
Yes, sir, same.
Time period is same. So here also,
Yes, sir, same.
so you see, time period is pi. Here also we are getting same type of waveform. Time period is pi, but only one difference is here. At a time, how many diodes are on in the bridge type rectifier?
Sir, 2.
2 diode. But in case of center tap, how many diodes are on at a time?
1.
1.
One.
So that will affect my resistance or not?
Yes, sir.
See, when you calculate, this one, we have to put 2 RF. Yes or no? Because 2 diodes are on at a time. For center tap, only 1 diode are on. So one diode contribute 1 internal resistance of RF. So 2 diode means it is in series connection. So 2 RF we have to put. So in place of RF, we have to put here 2 RF. This is the only change you have to do it. Okay. And for DC calculation, it is same, because ultimately across the load RL we are getting, and here,
This way, sir.
yes,
Sir, could you show the change once again?
change.
Yeah.
You see here one diode is on, here one diode is on. So this diode will contribute RF, this diode will contribute internal resistance is RF. So both are in series or not? So total resistance offered by this 2 diode is 2 RF. But in case of center tap, you see, let us go to the center tap. This diode is on, at a time this diode is off. So here it is only contributing RF for positive half cycle. Negative half cycle it is off, it is on, so it is contributing RF.
Yes, sir.
Now while calculating the AC power, what we are calculating? We are calculating I square into R. R means the total resistance. One resistance is due to load resistance and one resistance due to diode resistance. So as in case of bridge type, 2 resistance are on or 2 diodes are on at a time. So we have to put it here 2 RF in place of RF. Understood?
Yes, sir.
Yes, sir.
So everything is remain same, and here efficiency calculation also ideally you will get same thing, because see, if RF is less than RL, then 2 RF also much less than RL. So suppose I will take this is 10 ohm or 50 ohm and this is 1 kilo ohm, and here if I multiply by 2, say 100 ohm and 1k, still it is less. So 2 RF by RL also much less than 1. So you can also neglect as in case of half rectifier circuit. So everything will be same if I take ideal condition. But if you take practical condition, suppose in a question it is given that RF is 50 ohm and you calculate that one, then you have to follow this process. That means 2RF plus RL. If it is not given, internal resistance of the diode is not given, then you think it is ideal condition. So anyway, we have to neglect RF. So ideally it is 81.2%. But if you take practical condition, center type and bridge type, this is the difference. In place of RF, you have to put 2RF. So again, you just calculate all these things by taking 2RF, okay, and here 2RF, like that you can write. Clear? Now I give one question. Let us see whether you are able to solve or not. First we give for half-wave rectifier circuit, then we'll go for full-wave rectifier circuit. So all of you try to solve this one. A half-wave rectifier circuit is fed with 12 volt AC input voltage with diode internal resistance of 50 ohm. Find peak current, DC current, RMS current. Also find efficiency and ripple factor if RL is 950 ohm. So what is asking here? It is asked for peak current means IM, DC current means IDC, RMS current means IRMS, ITA, then ripple factor. These 5 things it is asked. So how to solve? What is given here? RF is given. So you cannot consider this is ideal condition or ideal circuit. We have to consider RF because it is given in the question. RL is given 950 ohm, okay, and AC is given 12 volt. So if AC is given, then you have to calculate, or you can write VAC is given 12 volt, then VM peak voltage will be, remember this one, it will be root 2 time of AC voltage. Whenever AC thing is given, AC voltage, then to find peak voltage you have to multiply with root 2, okay. So this is your VM. Then if you know VM, then you can calculate IM, voltage by resistance is your current. So how much it will, if you calculate this one, 1.4 into 12, so it will come as nearly 17 volt, okay. So
Sir, 0.0169 आ रहा है 0169
0.016 में कैसे आएगा? 12 into 1.4.
सर इसका नहीं, IM का वैल्यू.
ओ IM का वैल्यू, अच्छा. So it will be VM by RF plus RL, okay. 17 divided by 1000, it will be how much?
0.017, yeah, milliampere.
Milliampere, okay. If you not consider RF, then it will come as what you told. But here it is given means you have to consider RF. Okay. Then you calculate IDC. What is IDC? For half wave, this is Im by pi. I Rms, Im by 2. Yes or no? Tell me what is
Yes.
that? This is very simple, 8.5 milliampere, and 17 by pi means how much?
5.41.
5.1.
Okay. Now efficiency, how will calculate? We know that the complex formula you should not use here. You can simply use, because ideally what we have found out, 40.6 divided by 1 plus RF by RL, and we have neglected this term. So what we will do, 40.6 divided by 1 plus 50 by 950. You calculate how much you are getting. This percentage. 50 by 950 plus 1, 40.6, because whatever you have neglected you cannot neglect now, so directly you can put that formula and you will get I think less than 40 point you will get. How much you just exactly find?
38.67.
38.67.
67.
Now ripple factor, I Rms by IDC whole square minus 1. So what we have got, I Rms 8.5, this is 5.4 whole square minus 1 square root. I calculate this value for 1. We got 1.21.
1.2124.
1.21. So you see here we are taking practical case, so the efficiency is reduced a little bit. So this is the way how you can solve. Have you, all of you have written? Now let me change the question a little bit. So instead of half wave rectifier, I will take center tap full wave rectifier, circuit fed with, instead of 12 volt AC, I will write here
DC.
DC. DC क्यों देंगे भाई रेक्टिफायर में? Okay, 50 sine 200 pi t, and internal resistance let it be 50, and load resistance also 50. Now how to solve it? Any idea?
सर VRMS निकाल के कर ले.
No, it is asking for current. See how to solve it. Whenever you take any voltage function, like you want to draw, so how we are writing here, this is V equals to Vm sin omega t. So this Vm is what? Peak voltage. Yes or no?
Yes sir.
Yes, sir.
And omega t, it is given as 200 pi. So indirectly it is giving you Vm. So this is your Vm. Vm is 50, it is given. Like last time it is given 12 volt AC and we have calculated peak voltage by multiplying root 2. Here directly Vm is given as 50.
Yes,
Then
sir.
if you know Vm, then everything is simple. So Im is Vm by Rf plus RL. To find this one, then IDC, for IDC to Im by pi, just now we have seen. I Rms is Im by root 2. Then here 81.2 divided by 1 plus Rf by RL, and efficiency is, you just put whatever value you will get and square root and tell me what is the answer. First find Im. 50 divided by 950, 50 1000, so 50 milliampere directly you will get. 50 divided by 50 plus 950, so it will be 50 milliampere. Then IDC 2 Im by pi, tell me what is the answer.
So 31.8.
31 point,
Million.
83.
then RMS
22.50.
22.
35.35.
Now find efficiency. At 1.2 divided.
77.13.
77.13. So 70, nearly 77% we are saying.
Yes, sir. 77%.
Then ripple factor you find. IRMS by IDC I have written whole square minus 1 square root. I think it will also come as nearly 0.48. We check it.
.67.
स्क्वायर रूट करो, नहीं किए हो तो मिला.
Should
Yes, sir.
0.67
Yes, sir.
million.
18.
Okay. Now, if the same question I'll change to, instead of the center tap, I'll take this type, then what change you will do? Just tell me. You'll again do it, but now tell me what changes you will do.
2 RF.
Here in place of RF, it will be 2 RF. Here in place of RF, it will be 2 RF. Okay, that is the only change you will do. Okay, here it will be 2 RF, here it will be 2 RF. So little bit it will decrease, and here also the little bit decrement you will get. So these two type of problem today you practice. Next class another one problem I will tell. After that we will go for filtering action. PIV calculation and filtering action we will discuss in the next class. Okay, so these questions are very important. You will get definitely one question in the mid sem and one question in the end sem. Rectifier problem or rectifier derivation.
PDF question है sir.
Sorry.
PDF PPT there is question. Practice question.
PDF PPT में नहीं है. You can write. That's why I told you ना. You write the question. Otherwise assignment में मैं दूँगा. अभी तो नहीं है. You can write it.
सर हमारा फिजिक्स
हाँ हो गया
फिजिक्स का अटेंडेंस
just a minute I'll take. Give me just 1 minute. Okay, attendance taken. You can leave. Thank you.
थैंक यू
Thank you,
सर
sir. Thank you.
sir.